Let's say we have a problem like this where there's a block being pushed up an incline or a ramp, and it's being pushed up with some applied force, FA, F applied, which let's say is equal to 650 newtons, like that. And we know that the angle made with the ramp, this angle theta, is 15 degrees. We know the mass of the block. There's some coefficient of kinetic friction, so the block must be feeling kinetic friction. And what we're told, the last piece of information we're given, is that this applied force causes the block to slide up the ramp a distance of 3.0 meters. Okay, so it moves up the ramp along this incline 3.0 meters, like that. Now, we have been asked to find, let's say, what we're asked is to find the work done by each force, each individual force acting on the block. So to find the work done by each individual force, well, first we should start by drawing each of the forces on the block. So there's always weight pulling down, right? And, since we're talking about work here, I'm going to stop using W for weight, and instead I'm going to use Fg, force of gravity, just to avoid confusion. And the weight, the force of gravity, is m times g. There's the normal force, Fn, pushing up, which actually should extend higher up, but I don't want to run into my 3 meters here. But the normal force should be longer, the arrow length should be longer. And of course, kinetic friction pulls back because there's a coefficient of kinetic friction given. And the applied force pushes up. So those are the 4 forces acting on the block. What we now have to do is figure out what the work is, what work is done by each of these individual forces. So the first thing to notice is, remember, force and work go together. So work is a property associated with individual forces. So we will have a different force, a different work being done by each of these 4 forces. Right? This will have some work done, this will have a different work done, this will have a different work done, and likewise for Fk. So to get started, the first thing we need is the equation for work. That's W equals F d cosine the angle between F and D, which I sometimes notate like that, theta FD. Oops. The angle between F and D. And as we see, plugging in different forces will cause us, plugging in different forces here, will cause us to find different works. So first let's find the work done by, let's see, what should we do first? How about the applied force, Fa? Well, if we're finding the work done by the applied force, we have to plug in that force for F. So the applied force is 650. The distance that the block moves is 3. And then we have cosine of theta. Now, look at this. The applied force is up the ramp. The distance traveled is up the ramp. So the angle between those two things is 0. So you plug that into your calculator, and that's how you find the answer. And making sure you're in degrees rather than radians. Okay, I'm not going to find the answer because you guys can do that, but you know how. The next thing we're going to do is find the work done by a different force. Let's do kinetic friction. So the work done by the kinetic friction is equal to that force, Fk, times d, times the cosine of the angle between the kinetic friction force and d. So what we plug in for kinetic friction, we have an equation from last unit, which was mu times mg cosine theta, this is going to get confusing, times d cosine theta. And let me write theta FD here. Okay, now this is a little confusing if you plug in the way I've done, but that's okay, we can keep track of our angles. Mu is given, right? That's 0.26. Mass is given, that's 54. G is 9.81. This theta, right, cosine of this angle, is this angle, 15 degrees. Right? And then we plug in for D, the 3 meters. But then we have to plug in cosine of the angle between force and distance. And here we're looking at Fk. So Fk points to the left, down the ramp. And the distance is going up the ramp. The block moves up the ramp. So for this angle, we're going to plug in 180, since that's how many degrees, excuse me, that's how many degrees separate Fk and the distance. So it comes to this, 0.26 times 54, the mass, times 9.81, times the cosine, and this is so tricky because there are two different angles. Here we plug in 15, and I'm running out of room, so let me do this instead. I'm going to write D over here. So I'm writing the D term, I'm moving it over in front of mu, so this is D, 3 meters. And then the last thing is the cosine of the angle between F and D, right? This is an F up here, the angle between F and D. And that's 180. So that's hard to see, so let me write that over here as well. 180 degrees. And let me erase it from over here. So this equals the work done by the force of kinetic friction. Like that. And again, this is the cosine of the angle between F and D. Here is D, and then these line up. So this is tricky because we have to keep track of the two angles that we are multiplying by. But we can do that, we're advanced students. So next, I am going to find the work done by, let's see, there's two forces left. Let's do the force of gravity next. The work done by the force of gravity is equal to, of course, F times D times the cosine of the angle between them, like that. So, this is pretty simple. For the force of gravity, we can plug in mass times 9.81, as we know. D is the distance traveled by the block, and in every single calculation, that's going to be the same, 3 meters. Then we have to multiply by the cosine of the angle between the force of gravity and the distance traveled. So gravity pulls down, and the distance is up the ramp, as we've seen. So we have to find this angle here. We have to find that angle. Now, here's how we can find this angle. It requires a little bit of geometry, but if you take from this point, the center of the block, if you take that point and you draw the horizontal from there, so that this is parallel to this, then what we have now is theta right here, the same angle that we have here. So this equals this, which means that this is 15, because this is 15. So we know that this angle is 15, and we know that this is a 90-degree angle, because gravity pulls down, and the dash is the horizontal line. So down and horizontal make 90 degrees. This makes 15 degrees. So the whole angle between gravity and the distance traveled is 90 plus 15, or 105. So you plug in the cosine of 105 degrees. And what you'll notice is that this is a negative number. So you get a negative work being done by the force of gravity. And in fact, you saw the same thing if you plugged in the value and found the work done by Fk. Whenever the angle is bigger than 90 degrees, you're going to get a negative work being done. Okay, now the next thing we are going to do, and you can plug this in and find the answer, The next thing we're going to do is find the work done by the normal force. So we use the same equation. The work done by the normal force is the normal force times the distance traveled by the block times the angle between the normal force and the distance. So take a look, because before we plug anything in, before we start trying to calculate the normal force using mu and the cosine of theta, before you do any of that, notice the normal force points off the ramp like this, perpendicular to the ramp, and the distance is parallel to the ramp, or up the ramp. That means this and this, the normal force and the distance traveled, are at right angles to each other. So that's a 90-degree angle which we would be plugging in as theta. Theta would be 90 because Fn and d are perpendicular. The cosine of 90 is 0. So you can just say that this is 0 since the normal force is perpendicular to the distance traveled. And no calculation is needed. You don't have to go through the equation, right, where Fn is equal to mg times the cosine of this theta. You don't have to do that. All you have to do is realize that theta Fd, the angle between the normal force and the distance, is 90, which makes the cosine of 90 0. So that's how you solve this problem. And what we've done is we found the different works that are done by each of these 4 forces. Right? That's what we did.